So last time we were talking about changing rate, which is later we will call it the derivative, which is the same as velocity and the slope of the tangent line. But either way, the thing we eventually need to handle is going to be this process with this formula. Everything here is easy. It's just algebra. The harder part, which we don't know yet, is how to take the limit. How do you think about is h 0 or not 0? And how do we do the computations? That will be the main theme of the following chapter, chapter 2. Limit. Okay. Today, we just want to give you a really brief walkthrough of the simple concepts related to limit. So let's talk about the limit of a function. Definition. What do you mean by limit? Well, the notation is given by limit x goes to a, fx equals L. Here a and L are numbers. And what this one says is the limit of fx is L as x goes to a. Another way to say it, fx goes to L as x goes to a. Now, if you think about this definition, the average velocity equal to something as h goes to 0. That's exactly the same format we're trying to form here to solve the problem we want to solve. Okay? Now let's figure out what it really means and how to compute it. This one basically says your function value will be very close to a number when your x goes to a. The way to understand x goes to a is x is very close to a. Okay. How close? As close as you want. Which is, again, the fancy words we introduced last time. This is exactly the case we want to deal with. When something is as close as to, or as small as you want. That's how we understand this. Okay. With that in mind, let's do some computations. How do you find limits? Of course, our ultimate goal will be if I write down something like that and say, hey, go ahead and try to find what's the limit of this function at here. You should be able to, through some calculation, to tell me what this number is. That's the ultimate goal. Okay? The harder part is those kind of things usually are confusing. So first, when we learn something new, we always start with the one which is more intuitive. That is how to do it with graphs. Let's assume we already have the graph. How do we find the limit? Okay. For example, let's think about the limit of x goes to 2, x plus 1. Okay, what is it? Well, this is a simple graph, so I can draw it. It is a straight line passing 0, 1 with a slope positive 1, so it's something like that. Here's 1, here's 2. So basically what you're trying to say is, what is the function value of on this line when x is very close to 2, but not 2? Make sense so far? So just imagine you take a single line and covered this function here. So you cannot see what happens exactly at here. You cannot see that. It's covered. Good so far? But somehow you will try to guess what happens there by looking at what happens on the left and on the right of the line. So what do you think? Looking from the left, I will guess it's here. Looking from the right, I will also guess it's roughly here. Okay. Now let these 2 points go closer and closer and closer and closer to each other, which means my x approaches 2 to be as close as I want. I'm just going to guess the point is right here. That is on the function, which is 2 plus 1, which is 3. Make sense so far? That means when the function is nice, what you guessed by looking around is basically the real value. Okay, for example, it's almost like, I know yesterday it's 58 degree. I know tomorrow it's 59 degree. Okay, now I'm gonna make a guess. What do you think today's degree is gonna be? What's your guess? 58.5, 58.7, 58.6. They're all reasonable guess. Make sense so far? When things behave nicely. Of course, it's possible that today is 72 degree. By looking at before, looking at after, there's no way you can guess what's going on because anything can happen, right? But what we really care about is, how can I tell what's going on by looking at things around you without observing exactly today? Because it's not possible. I can only use information around it, but not exactly at it. That's what we're trying to do with limit. Remember, we need to tell what happens when you are close to 0, but not at 0. Close to 0, not at 0. Okay, that's what we're trying to do. Sounds good? That's the first easy case. There's nothing to talk about here. It's very easy. But with this example, you start to see something shaky can happen. For example, it's possible that I have some function. Judging from the left, judging from the right, I'm going to guess the point is here. But it's very possible that the point is here. Right? Then in this case, what is the limit? Again, you're trying to tell what happens to this function when things are close, but not at this point. Therefore, the limit should be here, even though the real function value is somewhere else. Make sense so far? Okay, so for that case, there's still no big deal. Cover it so you don't see anything. Judging from the left, judging from the right, I'm going to guess the point is here. And I don't really care where the real point is. I'm talking about limit when I'm close to you, not at you. Okay, so that is the limit. If we have a hole, we just pretend we didn't see this. We guess what's going to happen, and the limit should be here. Okay, that's the second case. The third case. Look at this point. And the graph looks like this. That's possible. Judging by college algebra, we call this piecewise defined function. On the left, you have one formula, one shape. On the right, you have a different shape. That's very possible. Okay. So now, how are you supposed to guess what happens here just by looking at points around A, close to A? Then it really depends which direction you're looking at, right? From the left, I'm going to guess the point is here. Right? From the right, I trace all the way down. I'm going to guess the point is here. Okay? Now I have yesterday, which is before. I have what happened after. Now how can I tell what happens right now? It really depends. Are they the same number? If they're different, I don't know which one to pick. My answer will be limit does not exist. Which way right does not exist for this case. Because on the left, I have one number. On the right, I got a different number. So there's no way I can tell which one is correct. Good so far? So for this case, what you really should do is you should check the left. You should check to the right. Okay, and hopefully they are the same. For example, checking from the left, it's this one. Checking from the right, it's this one. Then you very well have a limit, and the limit is actually where the 2 points overlap each other, right? So check the left and check the right. If they're the same, you do have a limit. If they're different, there's no limit. Okay, that's the third case. Still okay here? Can you have other cases? For example, what is the limit? X goes to 0, 1 over x. Let's just draw this one. Do you remember how to draw 1 over x? Let's just think about positive numbers. Okay, to the right of this quadrant. When x is big, this one should be small. When x is very small, this one should be huge. Right? That means when x is big, this one should be low. When x is small, this one should be high. How high can you get? Really, if you let x to be very close to 0, this one can be as big as you want. If you take x to be 0.00001, 1 over that is huge. But this one is even bigger. Even bigger, and even bigger. If you keep going on, you will realize this one goes to infinity as you get closer and closer to 0 from the right. Good so far? We call that thing a vertical asymptote. Something like that. Similarly, try the negative part. You will have something look like this. Now what's your answer? What's the limit of this function at exactly here? Well, it depends on which side are you looking at, right? From the right, what's the limit? Positive infinity. Starting from the right. Starting from the left, what's your value? Negative infinity. Good so far? Together, what's the limit? From both left and right. There's no limit because left and right does not agree. Similar to this case. On the left, you got one value. On the right, you got another value. They don't agree, so there's no limit. Sounds good? Okay, so this is the last case we will introduce, where we have a vertical asymptote. Okay, and then what your answer will be really depends on what's the shape do you have. If it's that, on the left, on the right, both positive infinity, your answer should be positive infinity. If they're both negative infinity, you should have your answer is negative infinity. But if one is up, one is down, one is up, one is down, your answer should be does not exist. Because even though you have infinities, you are not the same infinity. Okay, that will be the last case. Make sense to everybody so far? So normally we only have 4 cases if I draw out the function. The function may be really nice, continuous. Okay, then finding it is really easy. It's the same as the function value, the limit. Maybe the function is not so nice, but not so bad either. Then finding the limit is still try to guess it, try to plug in to the formula of these two sides and ignore what happens here, because it really doesn't matter. Okay. Now things get a little bit tricky if you have a jump. Then what you should do is check the left, check the right, and hopefully they are the same. If they are the same, we have a limit. If they're not the same, we don't have a limit. Finally, it's possible we have vertical asymptotes. And the principle is quite simple. Check the left, check the right, and see do they have the same kind of infinity. If they're both positive, check. Both negative, check. One positive, one negative, sorry, you don't have a limit. Okay, that's the 4 cases. I'm going to pause here and feel free to ask any questions. Try to sort those kind of things in your mind. Emma?
Can you just go over the first case one more time? I got kicked out of the meeting. Just like very briefly, can you do that one more time?
Yep, the first case is actually really easy. That is, if you want to know what happens here for my limit, basically cover it, you try to guess what's there, right? You cover it, so you pretend you don't see anything here. You just try to guess it by looking at things around it. Okay, you try to guess what the value is. And the good news is, what you guessed will actually be the real value. Okay, in that case, you can simply just plug in the number and get the real value, and it's the same as your limit.
Okay, thank you.
Mm-hmm. Randy.
Okay, if you go down to, I think
you are still, I cannot hear you, Randy.
Okay.
I still cannot hear you because now, yeah, let's try again.
Can you hear me now? No? How do I?
Seems like it's not working. Can you type your questions in the chat?
How about now? Can you hear me?
Yep, it's working, yep.
Okay, sorry. I got 2 different audio settings because I'm on Linux. So if you go down to the vertical asymptotes one, I just had a brief question. So you said if they're both positive or both negative, then I don't have to worry about it, then the limit does exist. What if they're, what if the rates of change are different so that they're both positive, approaching like a positive infinity or something, right? But they're going up at different rates. You see what I'm saying? Would they still be?
That's roughly what I can draw, right?
Yeah, like that, right? Like that. So is that still the limit exists?
Let me ask you a question. If I say the limit here is positive infinity, do you get confused?
Maybe. I guess I'm not. I guess I would have to understand further what positive infinity is.
Exactly, but what I'm trying to say here is your question is a really valid question. That is like,
right.
When you talk about the infinity, you really need to be careful about what you're looking at. Are you looking at the value, or are you looking at the speed things going to infinity?
Right, because with this, it might be approaching the same value, but if it's approaching it at a different rate, you see what I'm saying? How could, because the rates would be different. It would be similar to like the second case or whatever, the third one. I mean, you gotta jump.
Let me ask you this: say, let's not talk about the infinity case. Let's talk about a number case, right?
Okay.
You agree. On the left, you approach this number faster, and on the right, you approach this number slower.
Right.
But do you feel comfortable that it's still okay to say the limit is here, even though you go to the limit at the speed?
I think I do.
If you
because it's continuous.
Exactly.
But because it's continuous.
Exactly. So if you
there's discontinuity with the case that I just mentioned, so they're not quite the same. by what I can make sense of it.
I understand. I understand. Your question.
Similar, but not.
Let's say what I'm trying to say here is, you're talking about two things, right? At two levels. The first level is what is your value. Number two is how fast do you go to that value,
Yeah.
right? What I'm trying to say here is, if you're trying to do the limit, you actually only cares about the value, not how fast you're going there. Because if you care
Okay,
about
so the limits don't. For the limit, it doesn't matter what the rate of change is. That's for derivatives only.
Exactly.
Okay. So I get it.
Because
then.
I'm going to argue that if you care about the rate, how you go to a limit, then why don't you care? Why don't you care about the rate here?
Right.
Because it's going to the same
Right.
limit.
That makes sense. Yeah.
So
Okay.
that's
So the
why
limit would
that-
exist there.
Yeah.
But the derivative might not.
Have you taken calculus before?
Yeah, I've taken it before. I'm kind of trying to get a better grade this time around and refresh
What I'm
on
trying
it.
to say here is, are you familiar with integral?
Yeah, I'm familiar with integration.
Good. Your question will actually pop
At least
up
somewhat.
when you start to try to do an integral of this.
Okay.
Let's say this. This is y equals 1 over x, right? Now you're trying to integrate from 0 to 1 over x. So what you're trying to do is you're trying to integrate something which has opened up.
All of that, right.
In that case, how fast you approach really matters now. If it's too
Yeah.
fast, your integral is going to be infinity. And if it's too slow,
Yeah, it's going to be a giant integral versus, yep.
Yeah.
Okay.
But your question is at the next level, but not for now.
Okay. Okay.
Very good questions, though. Yeah.
All right,
So
so
let's
how do
say
I
here
lower
in
my
this
hand?
case,
Oh, yeah.
we only care about, do you end at infinity? Well, on both ends, it ends at infinity, so we're going to take it. Okay.
Sure.
Good. Other questions? Awesome. Okay. So everything we did was by graph. Graph is, of course, great. The bad thing about graph is you have to graph it. If I give you something fancy and I say, hey, please go ahead and graph it, you will say, I refuse because it's too difficult, right? So what we eventually want is just look at this formula. We will be able to tell the limit without having to graph it. But of course, they should be connected. So we have 4 cases before. Now let's do the exactly 4 cases, but this time without the graph, and see what we get. The first case, you have something really nice and smooth, something like that. Okay. Then what's your limit? Your limit is really your function value. It's the same. So I can write it down. If fx is continuous at a, which means it's nice and smooth, then your limit is really just your function value. They are the same, judging by what I draw here. That is the first principle we need to know. That also tells you what is the limit when x goes to 2, x squared is. Well, is x squared continuous at 2? Yes. Then just plug in. Your function value and your limit are the same. So plug in 2 in x squared, you got 4. Oh, sin x. What's the limit of sin x when x approaches pi over 2? Well, the graph looked like this. No holes, no vertical asymptotes, everything just behave as they should be. Then the limit should be the same as your function value. It doesn't get anywhere. So just plug in pi over 2. And hopefully remember, it's required. What is sine pi over 2? Good. You should reflect 1. If you don't, check the unit circle, try to review a little bit. You need to know everything about pi over 2, pi over 3, pi over 6, and pi over 4. Anything other than that, we don't have to worry about it. But for these 4 special angles, we will use it. Cool. So for continuous case, it's really easy. It's basically, if I have to say, it's just plug in. And plugging is probably the easiest thing you can do. So it's pretty easy. Now the second case, where you cannot plug in because you have a hole. Okay. When will you see something case like that in terms of formulas? Do you recall you have seen something like this before? Is it continuous? Well, just plug in 1. What happened? You divide by 0, right? Therefore, it's not continuous. You cannot simply just plug in. Can't do it. So what do you do? By algebra, we quickly reflect. The top can be factored out. According to a formula, a squared minus b squared equals a plus b times a minus b. Therefore, x squared minus 1 squared is going to be the same as x plus 1 times x minus 1. Okay, divided by x minus 1. Sounds good? Certainly we can do that. After that, what do you want to do? Do you have the urge that you want to do something? Well, same factor. I want to cross them out by canceling. Can you do that? Until, why can't we do that?
I'm not gonna lie. I do remember talking about that last year, but I don't remember the because are we taking out one of our factors, or
We're taking
I
out
don't
one
remember.
of our factors. See, let's say you got 3 times 2 divided by 2. Then we can cross them out and give it us 3, right? Because they have the same factor. That's what we're trying to do here. Okay. Maybe you have a concern. That is, you can only cross them out if both of them are not 0. If they're 0, you cannot cross them out, right? Then the question becomes, are they 0? It really depends on, is your x 1? Well, x goes to 1. Does it mean x is 1? Not really. It means x is close to 1. It can be 1.0001. It can be 0.9999, but it's not 1. As long as you are not 1, this is not 0. Then we are okay to just cancel it out. Therefore, basically what we're trying to say is this function here and this function here are literally the same, except at x equal to 1. Good news is we don't care about what happens at 1. We care about what happens close to 1, which means not 1. Then we're okay. After that, finding the limit of this is the same as finding the limit of this. Do you know how to find the limit of this? Let's plug in. Continuous? Good. Plug in, got a number. That works. This will help us handle this case. Okay. Let me wrap up what I just said. This is difficult. This is easy. Right? For this one, you just plug in. For this one, you cannot plug in. Good so far? Now what do? We change this one to this one because literally you guys are the same except for at this point. And I change this one to this one by crossing out the term which will cause trouble. Then this one becomes this one. Finding the limit here is the same as finding the limit here, but finding the limit at here is super easy. Just plug in. That's what we just did. Okay. Of course, to make it a quick menu, simplify by crossing out terms, then plug in. If you can't plug in right away, you simplify, and then plug in. Hopefully, after that, it will work. That's the second principle. Sounds good? Okay, if you can plug in, plug in. If you cannot plug in, simplify, then plug in again. Third case, something look like that. Now we have said this, it's piecewise defined function. That means we have something look like this. Okay. Now my question is, what is the limit as x goes to 1, fx? Well, do you know how to find the limit? Well, x squared, I know the limit. The limit is 1, right? 1 squared, which is 1. It's continuous, super easy. X plus 1 is going to be 1 plus 1, which is 2, which is also super easy. Good so far? The only problem we have for this case is, which formula are you going to use? If you use this formula, I know how to do it. If you use this formula, I know how to do it. Right? But which one are you going to use? That's the question here. Sounds good? Now let's think a little bit about what do you mean by two formulas? That means here is one. That means on the left, you have some formula, which is x squared. That means on the right, you have some formula, which is x plus 1. Okay? So what happens if I want to plug in 1? It really depends on, are you approaching this one from the left? Because if it's from the left, I should use this. Or are you approaching this one from the right? For that case, I should use this. Make sense so far? That leads us to think about, okay, when you talk about limits, when you have two formulas, we really need to tell which one are we talking about. This one is from the left. I should do this. I'm going to call this one the left limit, which tell me going from the left, I guess the point should be here. This one should be from the right. I'm going to give it a name, the right limit. Okay, this one tells you looking from the right, the point should be here. After that, what we really should care about is, do they agree on each other? If they do, we have a limit. And if they don't, we have a jump. We should say limit does not exist. Does that make sense to everybody? Okay, so for something like that, we have two formulas. We just need to figure out on the left, which formula should we use? Find the limit. That's the left limit. On the right, which formula should we use? Find the limit. That's the right limit. Hopefully they're the same. Then there's no jump. We have a limit. And if they're not the same, we answer right away, there's no limit. The limit does not exist. Sounds good? Okay, let me write them down. Now we need to define new terms. Something we call left limit and something we call right limit. Okay, both of them should be similar to this notation because we're approaching the same point just from different directions. So what we would do is we put a negative sign here to indicate it's from the left. And we put a positive sign here to indicate it's from the right. Okay. Then, after that, we can say the limit exists if these two are the same. And this one does not exist if they are not the same. That will be the third case. We do a little bit more work for both sides before we make the conclusion. All right. Let me rewrite the example before. Fx is this. We said this before, right? Before, I don't know which formula to plug in. No, I know exactly. Because if I'm approaching 1 from the left, I should use this. And if I'm approaching 1 from the right, I should use this. After that, on the left is 1, on the right is 2. Are they the same? Then limit does not exist. Because 1 does not equal to 2. Okay, that's the idea for this. Basically, left limit tell you what happens here. Right limit tells you what happens here. Okay, so when do you have a limit? When those two match. And if they don't, you don't have a limit. Okay, third case done. Fourth case, very easy to think about. Y equals 1 over x. We have vertical asymptote. Recall in college algebra or pre-calculus, when do you have a vertical asymptote again? That's when you have something, some number divided by 0. That gives you something huge. Do you have that case now? Well, if you plug in 0, you got 1 over 0. What is 1 over 0? Infinity, for sure. All right. That indicates we have asymptote case. If we have asymptote case, like we said, you check the left, you check the right, and hopefully they're the same infinity. If they're not, does not exist. Sounds good? Let's try that. What's the limit of 1 over x squared when x goes to 0? Okay, infinity, so I know vertical asymptote. I should check the left, I should check the right. Moreover, I already know they are going to give me infinity. Okay. The only thing I don't know is positive or negative. Sounds good. Now just figure out. Here is 0. Approaching 0 from the negative, that means you have something which is roughly like 0.001, something like that. Okay, you square it, you take a 1 over, that's this 1 over x squared. Number 1, this is huge, of course. Number 2, is it positive or negative? It's negative, but then you square it, it becomes positive. So the first left limit is positive. Sounds good? Similarly, for the right, you can easily see no matter you plug in positive or negative close to 0, both are positive because of this square. Are they the same? They are the same. Then limit of this one is positive infinity. If one is positive, one is negative, we answer no. There is no limit. Sounds good? Awesome. That's it. That's all the cases we have. Are these all the possible cases? Not really. There are more complicated cases. I can easily give you an example in the end. But these 4 will be the majority. We'll cover actually everything we will need in our lecture from now to the end of the semester. Okay, so that's the 4 possible cases. Let's wrap it up. First case, really nice. Continuous. And then finding the limit. You just plug in. Case 2, not too bad. We have a hole. Strategy, simplify to remove the hole, then plug in. Number 3, something piecewise defined. Maybe they match, maybe they don't. Possible jump. What do? We check the left, we check the right, and we try to see, are they the same? If they're the same, they're the limit. If they're not the same, no limit. Finally, asymptotes. Okay, then really, it depends on, do you have this case? Do you have this case? Do you have this case? Or do you have this case? Positive infinity, negative infinity does not exist. Does not exist. Sounds good? Question. What if you have this case? Does the limit exist? Not really, right? Even if one of it is finite, the other one is not finite, but I mean, left and right, they don't match, so it does not exist. Okay, so let's be flexible and clever about this. We didn't write this case down, but it's common sense. Anton, what's your question?
I had one question about the piecewise function. Let's say with the equation on the right side includes, let's say wherever they part, let's say that x is like 2, where the 2 different functions go the opposite ways. Let's say the right side includes that point, x equals 2, and the left side does not include x equals 2. Could you say the limit is still, or could you say that the limit is specified for the function on the right?
Let me ask you this question. You're basically asking the difference between these two, right?
Yeah.
Okay. For this case, what's the right limit? It's here. For this case, what's the right limit? It's still here. Okay. For the left case, what's the left limit? Here. What's the right limit? Still here. Can you see in both cases, the left limit and the right limit are the same, therefore they should have the same conclusion? Because the limit only depends on the left and the right limit. Since they don't change, then the limit answer don't change, right? And you touch something really fundamental here, that is what happens at 1, or let's say what happens at the equal sign really doesn't matter. That's exactly the case, right? So similarly with this case, right? What happens at this A doesn't really matter. It's what happens around you matter. So this is a very special case that piecewise function, do you have less equal or bigger than equal, doesn't give you a different answer. They are actually the same. Very good. Very good question. So the answer should be, actually they don't affect the answer because you literally don't care about the equal sign. All right, other questions before we move on to some exercises? Okay, when you go back today, try to think about what we learned today and try to rewrite my notes, because don't just rely on my notes. There's a lot of like side topics and things I draw here. You should be able to condense my notes of every single section to be below half a page. Okay, because if you just write all the table down and all the concepts and connection down, there are really not much of it. So try to learn things at a high level. Sounds good? I give you 4 things. Later, you need to just try to recreate the 4 cases and put them into your mind. Okay. That's everything we need to do for this kind of classes. Okay. Once you understand things to that level, you find each section only covers a little content. It's not much at all. All right, let's try some exercise. Number 1, what is the limit? X goes to -2. X plus 2. X squared minus 3. Well, let's just plug in. It's so easy to plug in, right? Worst case, it fails. Then we try something else. Let's just plug in. Did you have any trouble? No, then that's the answer. It's continuous. We can plug in. Number 1 done. Let's plug in. Zero, nice. 4 minus 6 plus 2, which is 0 over 0. Do you have trouble? Yes. Then simply plugging in won't solve it. We need something else. Okay. So cross it out. It's not working. Well, what else do you have? Did you get infinity here? 0 over 0. It's not infinity either, right? 2 over 0 is infinity. 3 over 0 is infinity. 0 over 0 is not infinity either. So possibly not vertical asymptote yet. So case 1, continuous, not working. Case 4, vertical asymptote, not working. Do you have a piecewise defined function here? So the only thing left is case 2, right? What is case 2? Oh, how do you handle it again? We simplify, then plug in. Make sense so far? This is our only choice. If this doesn't work, what happened? We give up. We go look for help. Okay? But for now, it's pretty clear. Let's try to simplify. The top is already very simple. The bottom, however, can be factored out. Do you see a common factor? Cross them out. It's safe because they're not 0. Can you plug in now? No trouble. Still no trouble. That's it then. That's how we handle this. Plug in. Number one, you cannot plug in. So not case one. Can you simplify and plug in? There's nothing to simplify. It's very simple. Not piecewise defined. Only 4 left. What is 4 again? Vertical asymptote. Do you feel like this is a vertical asymptote? I feel like so. It's infinity. Therefore, number 4. For number 4, we just need left. We need right. We already know it's going to be infinity. We just care about, do you have the same infinity or not? Okay. How do we know it's positive or negative? Let's just plug in. 3 minus. Here is 3. Here means from the left. Let's try 2.999. All right. This, if you plug in 2.999, give you something extremely small and a negative. Therefore, this has to be negative infinity. For 3 plus, we try 3.11000001. Plugging it here, it's easy to see it's positive. Are they the same? Then does not exist. Moreover, we technically have this case. On the left negative, on the right positive. Okay, we have 2 minutes left. We will stop here. Any questions regarding to the examples we have here, and we will do more tomorrow. All right. 2.2 is basically over. I am going to open the web work. And because our office hour is on Tuesday, so I'm going to make the first homework 2.2 and 2.1 due next Saturday. So you have a long window so you can go and ask questions during the office hour. And also, if you find anything challenging in the homework, you're very encouraged to bring them to class. So at the beginning of the class, from now on, I will ask, is there any questions from the homework? So if you have anyone, just bring that thing to class. Okay, in that way, I can go over more examples in class so everybody can see it. Sounds good? Awesome. Okay, that's all for today. I will stay here for questions if you have. Otherwise, feel free to leave. Aaron?
So if you like ask to find the limit on, like, let's just say exercise 1, would the
Which, say it again, find the limit at what?
exercise 1 that we did, the first exercise one we did, if you like asked to find the limit, would the limit be 0 then?
You plug in, you find a 0,
Okay.
and you didn't see any trouble, then that's the limit. Yep.
Okay.
Yep.
Okay.
Emma?
So for the 4th example, when we have the vertical asymptotes, I still don't really get how we figure out like if they're positive or negative infinity when we plug in like super close on each side. If that makes sense.
Let me do this one. Let's do it step by step.
Okay.
Do you understand why I picked 29999?
Yes.
Cool. Then we just need to roughly, we cannot really do it because technically it's not 29999. It's something close, right? So let's just do 2 over 29999 minus 3. What do you think that thing is going to be? Something small.
Small number.
Positive or negative though?
Negative.
2, because it's 2.999 minus 3, right? Therefore, this is a negative huge number because 2 over something give you huge, but you still have a negative sign.
Oh, we plugged it into that thing. I didn't know that's what we were doing.
Oh, then yeah, we plug
makes
that
sense
thing
now.
in because x is 3 minus,
Okay.
right?
Okay, I didn't realize that. Okay, that makes more sense.
You got it.
Got it now. Thank you.
Cool. And awesome. Adam,
It's unrelated, I guess, to the lecture per se.
Go ahead.
But the extra credit problems for like, I guess I didn't see if there was any for this first section. I didn't actually look at that, but I assume those would be next Saturday as well.
yep. If 2.2 is web work is due next Saturday, then the bonus point for
Bonus points.
2.2 will be due the same day, same time.
Okay.
Yep.
Cool. Thank you.